Hello, 11th graders. We are moving on with our kind of wrap up of geometry unit. We are moving on from the applications of trigonometry for the area of a triangle. And we're going to talk a little bit about circles and some things that we might be asked to find at some point with circles. So we've got this idea of sector area. And arc length. And really the big idea with both of these is that we're talking about a fraction of a circle. When we're talking about a sector area, we've got our circle, we've got just like a slice of pie or a slice of pizza cut out of this circle, and we want to know what is the area of this sector, of this slice. That's what we want to know. And it's the idea of it's a fraction of the total area. So it's a fraction of the area. Well, fraction times area would give us that idea of the fraction of something. So we need to find all of those pieces in order to then find the area of the sector. So the fraction here is indicated by this what we call a central angle, because it's the angle that's in the center. So this central angle is a part of the whole circle. And so that's the part over the whole aspect of fractions that we hear a lot, theta. The whole, what it's out of, is a circle amount of degrees, 360. So your theta, your angle right here, is how much of that circle are we looking at out of 360. And then it's just times the area of a circle. If this was a third of a pizza, we would just take a third of this area, right? And how we would know it was a third is that this central angle would be 360 divided by 3, which is 120. So it would be 120 over 360, which would be 1/3 of a pizza. So that's how we figure out this fraction area. Pi r squared is the area of a circle. Many of these pieces are available in your formula packet. I'm not entirely sure whether it's available, whether sector area is in your formula packet. If it is, awesome. If it's not, there's really no need to panic, as long as you realize, again, it's just the fraction of your total area, and that's it. You just need to figure out what percentage of this entire circle you're looking at. But there's definitely the area of a circle. I know quite a few of you probably feel stressed out about which one's pi r squared and which one's 2 pi r. Use your formula packet and just know for sure, because that's easy points that's available to you on your formula packet. So if it's there, just use it. That guy should be out next to you all the time. Oh, r is your radius, so that's this length, which is the same as this length right here. Now, arc length is also a fraction. It's a fraction of the circumference. So again, we're talking about the like a sliver of or a part of this circumference. And so let's say, for instance, that I wanted to talk about that arc length right there. Well, even if we just see it as an arc length in a situation that looks like that, we know that that arc is part of a bigger circle. And so we have to compare it to what would be the original circle. We still have theta and we still have a radius, and we're just saying, okay, well, it's just a fraction of the circumference of this circle. And how we know what fraction of the circle it is again by looking at that central angle, so theta over 360, and now just times the circumference of the whole circle, which would be 2 pi r. Again, if this is something that stresses you out, or something that you just notice that you make the mistake a lot, it is not something that needs to be mistaken ever again, because you will always have your formula packet. Just double check. There's nothing wrong with double checking. All right, let's go ahead and put this into practice. Suppose you have a pizza with a total area of 120 centimeters. The pizza is cut into 8 equal slices. So if we have this idea of a pizza cut into 8, let's say, equal slices, if the area is 120, we want to know how much one slice is if it's cut into 8 slices. So pretty straightforward. We take this guy and we divide it by 8, which is the same thing as saying 1/8 times 120, and that is 15. And it does say centimeters squared. What is the total area of 3 slices? So we take that 15 and we multiply it by 3, which gives us 45 centimeters squared. So that's just the idea of a sector, is you're taking a fraction of that whole circle, and then just how we determine that fraction normally, whereas here it just told us, hey, it's 1/8 of the whole circle. How we determine what that is we solve for this angle right here. And we would do 360 divided by 8, and it would give us an angle, and so that's something that we could do. But just this is the general idea, is you're just finding how much it is of the entire area. So then here's a more IB-like question. On golf courses, the grass is carefully watered to make sure that the grass receives neither too much nor too little water. On a certain area of a golf course, a lawn sprinkler is set to spray at an arc of 150 degrees with a spray distance of 3 meters. And they gave you the image there for you to be able to work off of. And we want to calculate the area of the grass that is watered by the sprinkler. So we want to calculate for this area. So it's just a fraction of your total area. So we know we're going to do theta over 360 times pi r squared. And theta is equal to 150 and r is equal to 3. I know this seems like a lot, but I guarantee you there are going to be problems in the future, if you haven't seen them already, where you are not going to know where to start. And I would recommend just writing out a formula and knowing what variables you do have and what variables you don't have is a really great way to kind of just get your mind wrapped around what's going on. So I think it's a good habit to get into, even if you think it's a little extra right now. I think it will help. Okay, so 150 divided by 360 times pi 3 squared. A word of warning before I ask you to calculate this. Please, 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 please make sure that you use the actual pi symbol in your calculator. Do not type 3.14. It will not work. You need to use the exact value in your calculator. If you don't know where it is on the TI-84, Google it, and some nerd on the internet will tell you where it is. TI Inspire guys, you click this. Hold on while my computer wakes up. You click this guy, and then this is what shows through, and then you press enter on the pi symbol, and then it brings it in. You press enter, and it says, okay, hey, that's pi, but it has the exact value of pi in your calculator, as about exact as your calculator can get it. Okay, with that word of caution, please go ahead and tell me what you got for the area of this sector. Multiplying this all out, since I did not tell you how many significant figures, you should go ahead and always assume 3. It is 11.8 meters squared. Let's move on to the next problem. Some airplane routes come very close to flying over the North Pole. Oh man, I really struggled in typing this. The route from Dubai, UAE, to Seattle, USA, comes very close to the North Pole. In this case, the distance of the flight can be estimated by the arc length. So we're talking about the path flight, and the distance that's going between Seattle and Dubai. Given that Dubai's airport is 25 degrees north, not bearing its latitude, longitude, just in case that was something that you thought, that's not bearing because it doesn't have the 3 numbers. And it doesn't say bearing. And Seattle's airport is at 47.5 degrees north, and they give us a diagram, which is really nice. Estimate the length of the flight between the 2 cities. So we want to know what this flight is, what this distance is. So this is arc length. So we know that arc length is equal to theta divided by 360 times 2 pi r. We want to know what theta is, and we want to know what r is. And it does tell it to us in so many words. It says that the radius of the Earth is approximately 6,370 kilometers. So I'm going to go ahead and plug that in for the radius. But we do know, okay, so this is a good reason why we write this out, is that we want theta for our arc length, but we don't necessarily have it right away. This is the theta that we want. This is the theta that we want. It's that central angle again, and it's the central angle that creates the slice that cuts that circumference or cuts that arc length. Well, it cuts the circumference too. So we want to know what this angle is. It has to be this angle in order for it to be used appropriately in order to find that arc length. So go ahead and see if you can figure it out and tell me what you get for theta. You should have gotten that theta is 107.5. 107.5. And what you should have done is 180 minus 47.5 minus 25. So these guys all add up to 180, all of these angles right here, because they create a line. Because it's the equator, they're talking about building off of the equator. So we know that that's a line that cuts through there. And so we know it all adds up to 180. So we just subtract from 180 and we get 107.5. Now we have all the information we need in order to solve for the arc length. Go ahead and tell me what you get. Plugging in 107.5 divided by 360 times 2 times pi times the radius, we should have gotten 11951.578. And we will do 3 significant figures here. Even though 3 significant figures, it seems like a massive rounding, because this is your first significant figure, your second significant figure, and your third significant figure. Looking at the number afterwards, it's 5, which means that this 19 idea rounds up to 20. 12000 kilometers. It's a big rounding, but if you think about it, the difference between this number right here and this number right here is actually not that big of a difference. And it still gives us approximately the same amount of information. So 3 significant figures are always a good thing to go to. Assuming that the plane travels at a constant elevation of 10 kilometers above ground level, estimate the actual flight distance. So this was just measuring the distance between these two guys on ground level, but planes are above ground level, which means that your radius is increased by 10, which means that your path is this idea of 10 kilometers above what that path is. So you can see here that arc length is going to get longer as a result. Now, this is very disproportionate, right? If this is 6,370 and this is 10, it's a little disproportionate, but I do want you to get the idea is that since we're further up, that arc length is going to get bigger. So we're going to calculate that now. We still want to solve arc length, so we still want theta over 360 times 2 pi r. Our theta is still the same. It's that 107.5 that we calculated for earlier. Notice that here is where the radius changes, and our radius just gets extended a little bit more by 10. So our radius then becomes 6,370 plus 10, which is 6,380. So now we have all of our missing pieces, and now we can solve for our arc length. Go ahead and tell me what you get. Plugging it in. We should have gotten 11970.34. Rounding that up to 3 significant figures, 1, 2, this is the third significant figure. Looking at the number after it tells us to round up. So again, it becomes 12,000 kilometers. And so this is just to show you that the radius is already so long for the center of, or for the radius of the Earth. It's so long that adding another 10 kilometers is actually a pretty minute difference in terms of the distance that we're going to be traveling from those two cities in terms of on the ground versus in the air. That difference actually doesn't change that much. That if we're rounding it to 3 significant figures, it ends up rounding to the same thing. And really the only difference between these two, that's less than 20 kilometers difference there. So now you know.